Hi all, welcome to a video on BJT current mirror and Wilson mirror. Now this video is not a part of the current playlist that I'm creating, that is semiconductor physics of the PN junction. Nevertheless, I had the notes of current mirror and Wilson mirror with me for quite some time, and this is a circuit that is misunderstood. I have seen confusion coming up repeatedly when it comes to explaining how a current mirror works. So I thought that I would share the notes with you and have a discussion on how a current mirror or a BJT current mirror in particular actually works. When we get into the actual course, after the playlist on PN junction semiconductor physics, we will dig deeper into current mirrors and we will talk about more compensation methods in a current mirror. So moving along. So as you can see in the circuit diagram to the left of your screen, you have a current mirror essentially looks like this. You have a left arm and a right arm in the circuit, and the left side of the circuit is used for programming the current. That is that is denoted by the resistor that I have named as RPGM. You have an NPN transistor, so this is an NPN current mirror, and surprisingly the collector and the base of this particular transistor is shorted, and that is what is the speciality of a current mirror, and there's a lot of confusion around this particular connection. On this end is the load side, so the current amount of current is decided by this side, that is the program side, and the current that is decided by the program side actually flows through the load, and the load is, for even if the load changes, the current is supposed to stay the same. So the current is supposed to be held steady even when the load varies, but that is not the case, as we shall see. So we will be doing a study of the early effect as well, which will give you an idea that this is not the case. So we have two transistors. One important fact about the current mirror is the transistors have to be identical, and since they are on and they'll generally be in the form of an integrated circuit, they'll be on one single die, so temperature differences, the problems arising due to temperature differences are taken care of in this case. So the temperature rises or falls equally in these two transistors, compensating for temperature effect. So a current mirror makes it easy to link currents as written here in a circuit, so matching one current to another. So a current mirror can also show a very wide output voltage compliance. So in a circuit, if you have multiple stages and you need to match the current between one stage and the other, right? So you have multiple stages and one stage has to match the current for the next stage, and so on and so forth, then a current mirror comes into play. So a current mirror is generally a 3-terminal device where an input current is fed into one terminal, and the current in the output terminal is a multiple of the current of the input terminal. So ideally, if you say, in this case, you have a 15K resistor and a 15 volt supply, so you are expecting a current to be around 1 milliamp, assuming that the node N2 will be holding a pretty low voltage. So it will be close to 1 milliamp. So if this is 1 milliamp, this also has to be the same. So input current is fed into one terminal, and the current in the output terminal is a multiple of the current of the input terminal. So it could also be designed in a way that the output current is a multiple of the input current. But in this case, the current gain is unity. So whatever current you have here, you will have the same current here on the load. So if the current gain is unity, the current is reflected from our program to our load, and that is why this device is called a current mirror if it has a gain of 1. the same thing described here. So you have the current going in the, say, left path, and the current value that we are programming for is approximately 15 volt by 15k, that is VCC or V1 by RPGM. Okay, so roughly about 1 milliamp, and what we see here is the current is getting reflected and it comes here, so it's mirrored. So as I said, change in the load resistance also should ideally keep the current constant. That's not quite the case. So before jumping into details of a current mirror circuit, we will discuss some transistor properties which we will use to analyze the current mirror later. Okay, so here to the left of your screen you have a typical NPN transistor. So you have a base current flowing into the transistor in the base. To the base you have the collector current and the emitter current comes out. So it's base current plus collector current is emitter current, as we all know. There's a voltage drop across base to emitter which we call as VBE. So there is a very well-known relationship and this is the relationship that I will eventually derive in my semiconductors playlist, semiconductors of the PN junction. I'm currently in the quantum physics part of semiconductor physics, but eventually I'm going to come here. So we know that there's a logarithmic relation that VE has with the collector current, and that is IC, which is the collector current, which is equal to IS e to the power of VBE upon VT. I'll let you know what IS and VT are. VB is the base emitter voltage, which is this. So if we take log on both sides, okay, so we take log base ln, so it's ln IC equal to, of course, ln IS plus ln e to the power of VBE by VT. So it becomes ln IC minus ln IS. Okay, I'm just rearranging the term, and then ln e to the power of VBE by VT becomes VBE by VT only because ln e is 1. So this is the final relationship. We have VBE equal to VT ln IC by IS. Okay. So IS is the current used to describe the transfer characteristic of the transistor in the forward active region. Okay, and VT is the thermal voltage and is measured to be about 25 millivolt at room temperature. Now, we will not deal too much with IS and VT here. We are not calculating IS and VT anywhere in this particular discussion. Nevertheless, these are the terms that you should know about. And of course, there's another relation which is IB equal to IC by beta. This beta forward is the forward current gain, which is something that you are aware of. So let us briefly study what we call as the early effect. So the early effect is the slight change in collector current with change in collector emitter voltage. So if you change VCE, the collector current doesn't stay steady. So the collector current is going to change. Okay, so what basically happens is greater the VCE, higher the collector current. So there is a relationship between VCE and collector current. So that is a problem we face with simple current mirrors, and to mitigate that we have to use the Wilson mirror. So we will be explaining that as we move along. So you have, so this is the width of the base, this is the width of the collector depletion region, not the whole collector. So the collector goes this way, emitters here, and you have the base. So basically what happens is when the VCE increases, so I'm trying to explain that in the animation here. So when VCE increases, the base, it squeezes the base basically. So the collector depletion region increases when VCE increases, it squeezes the base, and because the base is squeezed, more collector current flows actually through the base. So the animation is to show that. So collector emitter voltage, it becomes bigger. So when it becomes bigger, there is a change in collector current because there is a change in the base width, and this phenomena is called the base width modulation. So remember this because This is very important when we go into the Wilson mirror. And early effect is more prominent for higher B, because higher the beta, that is thinner the base. So thinner the base, greater the, so thinner the base, and if the collector depletion region increases, widens because of increment in the VCE, the narrowing of the base is greater. In the sense, the narrowing of the base is same, but since the base is thinner, the percentage of the base shrinking is much higher. So obviously the current increase is much steeper for higher beta. Now we will analyze a basic current mirror circuit using a BJT. So we will not get into FET right now. We will get into FET when we come to the main course. So we will look at the program side of the circuit first. So it's kind of a repeat. I had talked about it a little while ago, but let's go through it again. Here we are going to actually talk about how this circuit starts up. That is right from power on to where it goes stable. Okay, so this is very misunderstood. This part of this stage of the current mirror is quite misunderstood. So as we see here, like in the previous case, we have our program, our load, collector and base shorted. We have two transistors which are of the same. Okay, so that is very important. And let's assume that the circuit has just powered on. That is, the supply is given right now. So at this point, when the supply is given, you have Q1 and Q2 in the off state. So the transistor is still not. So these transistors usually operate in the forward active region, but as of now, the transistor is in the off state. So that's what you can see here. So we see that the collector, and also one thing is to notice that the base is shared between these two transistors. So whatever base emitter voltage you have here, you're going to have the same voltage here. Now what happens is, so now the Q1, Q2 are off. Okay, but once the power is connected, there is a flow of current through here. That is, it flows through here, this point, and goes through the short, because it is unable to flow through the transistor now because the transistors are in the off state, and it takes this path. Now once it takes this path, there is a voltage drop VBE across both the transistors here. So this current that comes through, okay, is say this current is 1 milliamp, and this gets again split between the two transistors, okay, and it turns on the two transistors. So it powers on the transistors Q1 and Q2, and due to the base emitter current flow, there is a voltage drop VBE as we spoke of. So let us not worry about the value of VBE yet. Let's say that it's between 0.6 and 0.7 volt. So for now. Now, since the VBE comes in, a few things happen. Because of the VBE, as we saw in the equation previously, that's the relationship between IC and VBE, the collector current starts flowing in both Q1 and Q2. And so the VB which is shared between Q1 and Q2 also appears at point A. So this is very crucial. So when the collector current starts flowing, you have a VBE drop here. But this VBE, since it's just shorted, also comes to point A. The moment it appears at point A, a few things happen. Okay, I hope you're following till now. So now a collector current IC starts flowing through both Q1 and Q2, obviously, right? Because these transistors are turned on, so it starts flowing because this VB that comes up is causing the collector current to flow. Now we will see that now it's a known fact that VCC minus VB, that's a simple V1 minus V2 equal to IR relation. So we have VCC minus VB equal to whatever current is flowing through here. So if I say I program into R program, so the VCC minus VB equal to I program into R program. Now I program, since the current is splitting up here, so we have a part of the current going through IC and we have a part of the current going into the base, right? So it is VB equal to IC plus IB into R program. So this is I have been a bit careless here. So it should be basically IB, whatever IB is this part, so it should be 2IB. You can say that this IB is kind of getting split up into two parts, but nevertheless, let's say it's IB now. So VB is VCC minus ICR program. I'm just rearranging the terms. I'm doing nothing else. So we get this relationship. Now if you see that if you increase IC, it causes a negative feedback and pulls down VBE. That is, the moment IC increases here, it takes away from IPGM, so this current decreases. Now this is not the same as the relationship that we saw, that is IC equal to IS into e to the power of VB by VT. This happens because of the short. This happens because of the short, and these, so we should be careful. We should not mix up between those two. Okay? So we see that the increment in IC causes a negative feedback and pulls down VB. Okay? So since the current reduces, the VB comes down. The moment VB comes down, IC2, we call it IC2 here. So the IC here, or IC2, goes down. So IC2 goes down because VB has gone down. But this time it is due to this relation. That is VB equal to VT ln IC2 by IS2. Whatever we saw previously, we just putting suffix 2 because this is Q2. Okay, as we have written here. Once IC gets pulled down by the equation, we have VB by the relation VB equal to VCC minus IC2 R program minus IB R program. VB again goes up slightly. Now, and this keeps on happening. So there's a balancing that keeps on happening, as you will see. VB keeps reducing, IC keeps increasing, and then IC decreases, VB increases, and there's a balancing act happening between the two until this condition is reached. That is VB equal to VT ln IC2 by IS2. So this is when the current starts flowing steadily. And so that time the VBE becomes steady. So when the VBE becomes steady, obviously since the VBE is being shared by both the transistors, the IC1 also becomes steady through the load. So this is how the current steadies in a simple current mirror from power on. And obviously, as I said, since it shares the VBE, IC1 and IC2 becomes identical. Another effect of shorting the base and collector for Q2 is that we see that the voltage comes back here, right? So say 0.6 something, between 0.6 and 0.7, if the voltage comes here, it comes here to point A. So between VCC and point A, since this voltage is low enough, lesser than 1, so we can actually, when we program the circuit, we can estimate the we can adjust the resistor in such a way that we get the current that we need, because we know that finally the voltage is going to settle somewhere between 0.6 and 0.7. This can also be thought of as a current source. So imagine that if there is a current source, that is the circuit preceding, there has to be a current matching done, and there is some current flowing in here. The same thing happens. That is the same phenomena that we were discussing about. And since VC is it helps in programming the reference current, as VC is a known quantity. So let's get onto a demo on a simple current mirror. Let's get started with the demo for the simple current mirror. I'm using Ngspice for the simulation here. Ngspice is an open source multi-platform spice simulator for electric and electronic circuits. I will leave a link to the Ngspice page in the description below. On the right of your screen, you can see the circuit of a simple current mirror. For those of you not too familiar with spice modeling, to convert this circuit to a netlist, you need to write the circuit in the netlist as components between nodes. As you see in the circuit diagram, we have nodes N1, N2 and N3, using which we can write the entire netlist for this simple current mirror. Coming to the netlist to your left, you can see that the components have been placed between their respective nodes. 0 happens to be the ground. The convention is the component followed by the nodes in between and the value of the component. So the voltage source is between N1 and 0 and the value is 15 volts. The programming resistor RPGM is between nodes N1 and N2 with a value of 15K. This resistor decides the current that needs to be mirrored through R load. In this case, our intention is to have 1 milliamp run through R load. Both the transistors are in forward active region. R load is the resistor which will have the mirrored current running through, and ideally the changes in the values of R load should not change the current set by the programming branch, which we shall see later is not the case. QPGM or Q program is a transistor on the programming side, and for SPICE, the convention for description of the nodes it's connected to is in the order of collector, base and emitter. Thus, it's N2, N2 and 0, 0 being ground. N2 is repeated because for a current mirror, the collector and the base is shorted, as you can see in the schematic. The transistor Q load is connected between nodes N3, N2 and 0. Since we are using the 2N3904 NPN BJT, the SPICE model has been downloaded and pasted here. So whatever name you mention after the dot model should be in the netlist. I have named it 2N3904, but you can call it otherwise. The next few lines are instructions to the SPICE simulator. The op command simulates to calculate the DC steady state values and show the values on the screen. We will be doing DC steady state analysis for all the demos in this video. Now let's run the demo. Coming to the output, we can see that the transistors and the voltage source values in steady state have been displayed. We see that the IC for both the transistors are very close to 1 milliamp as intended. Now let's change the value of RPGM or R program to 7.5K and R load to 7.5K with the intention of doubling the current through R load. Let's run the simulation again. As we can see, the current has nearly doubled in both the arms of the circuit. Now let us lower the value of R load to any arbitrary value, say 3K. We see now that the current through Q load is holding around 2 milliamp as intended, but we still observe a slight increase. Okay, so now since after the demo, let us see what happens what actually happens. So let us see what actually happens when the R load changes. So when the R load changes, the VCE for transistor Q1 changes, and hence the I load actually will change. Okay, so even though this current is constant, while if R load changes, okay, for the circuit which needs the current to be constant, we still see that there is a change, and that happens due to the early effect that we have already discussed. Now you would have seen the VCE versus IC characteristic curve of a transistor in your curriculum, right? So the slope of the curve that you had seen is actually due to the early effect. That is, when VCE changes, we see some change in IC. Due to the early effect, it makes this mirror not so ideal for use, because we are not getting an ideal current. It keeps increasing, so we have to find a way to stabilize it, okay, which will be done by the Wilson mirror. One of the ways. Okay, there are other ways of doing it also, but Wilson mirror is one of the ways of stabilizing the output current. This is what we talked about. This is the VC versus IC curve that you would have seen in your courses, in your curriculum, where with increasing VC you would see that these curves kind of, they're not parallel to VC axis, x-axis, but they slightly go up, and this slope is, you will see that this slope is variable. It varies from transistor to transistor. Higher the beta, you will see that the slope is steeper, because higher the beta means the base width is narrow, and then and because of that it exhibits greater early effect. Now if we are trying to figure out, so any slope on this curve is basically del IC by del VCE, right? So if we take one point on all of these curves and we extrapolate it back, it comes and converges on a point on the x-axis, and this is a voltage which is called the early voltage, and it's the meeting point of all the tangents. So the tangent is basically the slope of that particular at that particular curve, right? So, and we will study more about early effect in our future electronics course. So VA is called the early voltage, and for the transistor that we are going to be using, the early voltage is going to be about 130 volts, I think, 100 to 130 volts. So let's get on a demo with early effect and see how it affects the I load. In this simulation, we will be using the same circuit as the current mirror, but will increase R load from 0 to 15 kilo ohms in steps of 1 kilo ohm and observe the change in the current through R load. There is a little more script that has gone into the netlist, which does the DC steady state analysis in a loop each time, incrementing R load resistance by 1 kilo ohm. The 5K mentioned in the circuit description does not matter since we are altering the resistor value inside the while loop. Now let us run the simulation. We can see that 16 sets of DC steady state values are output for the increasing resistance values as per the while loop. The early effect becomes evident here. Even though current I RPGN stays almost constant around 1 milliamp, the current IR load changes from roughly 1.1 milliamp down to 0.9 milliamps. So the change of current is about 1.1 minus 0.9, which is about 0.2 milliamps. Now let us see the change in the collector emitter voltage of the Q load as well through these iterations. VCE is a VBE minus VBC as we know. Since VCE is not directly mentioned in the output, we calculate VCE like so. So we see VCE varies from roughly 15 volts down to 0.8 volts for a current change of 0.2 milliamps. This is about 20% deviation from the intended value of 1 milliamp. So we see the early effect in action here. Mitigate early effect. We have the Wilson mirror. So Wilson mirror is basically a third transistor that we add to the output transistor here, and that transistor mitigates early effect. Now this looks a bit different. This circuit is shorted towards the load side instead of the program side, and that is because of this transistor. So I would like you to follow the description for the simple current mirror. We had discussed about the startup of that particular current mirror, and I would like you to work on this particular circuit as an assignment and find out how this particular circuit stabilizes. We will assume that this mirror is at steady state anyway, because assuming that a steady current is flowing and now R load changes for some reason. So we will see that even if R load changes, how this Q transistor handles the early effect. So basically what happens is, if you see when R load changes, the collector emitter voltage of the Q check, that is the the transistor that is supposed to be checking the early effect, there is a wide variation of VCE. But even though there is a wide variation of VCE across this transistor, the Q load transistor does not see that variation because this value does not change much, and since the VCE of the Q load does not change, the collector current, so since this value does not change much, the load current does not change. So that is the role of Q check. So this changes a lot. However, this does not cause a change in the current because this transistor is only a pass-through transistor. It does not drive the current. It does not decide the current. It is just a pass-through. So this transistor actually takes the hit of the early effect where the CE increases widely, say from 0.7 volts to say around 14 volts, but it saves this transistor. So this transistor is not exposed to that voltage variation. So this transistor is able to keep the current constant. Now let's get on to a demo on Wilson mirror, and this will complete today's video. In this simulation exercise, we have the Wilson mirror schematics. We add another 2N3904 transistor to the circuit and will check for the change in VCE against IC for Q load. The netlist has changed a bit due to the addition of a third transistor. The only change between the previous netlist for determining early effect and this one is that the node names have been changed accordingly. Rest of the netlist is almost the same. We have just added the new transistor to check its steady state response. This is also calculating the steady state response for 16 values of R load as previously, starting from 0 through 15K. Let us run the simulation now. We can see that 16 sets of DC steady state values are output for the increasing resistance values as per the while loop, like the previous simulation. Let us check for VBE and IC for Q load in this case. Let's also keep an eye on Q check, that is the new transistor that we have put in. The new transistor inserted to mitigate the early effect. We now notice a change from the previous simulation. The collector current through Q load seems to change far less. In fact, the VCE value also seems to stay nearly the same. We also see that the current through Q check is slightly higher than Q load, since a part of the emitter current of Q check feeds the bases of Q program and Q load. In this case, we see that the IC of Q load changes only about 0.001251 milliamp as against 0.2 milliamps we saw earlier. So the Wilson mirror is definitely helping to keep the current steady. The change in VCE is also observed to be only 0.006 volts. Now if we observe the VCE for Q check, we see that it changes widely from about 14 volts down to 0.7 volts, almost similar to what Q load was facing without the Q check transistor in the previous simulation. So we see here that Q check takes a hit for the wide range of VCE. But since it is just a pass-through transistor and does not decide how much current flows despite the change in VCE, it does not influence the current change as per the early effect.